Hello everyone, welcome to this video on logistics regression. So we've come a very long way. We've started from introduction to statistics or data analysis. We've done descriptive statistics. We've gone through introduction to comparative statistics. We've gone through the different comparative statistical tests like chi-square, like ANOVA, t-test, Pearson correlation. So we've gone into regression analysis and we've done the introduction to regression. We've done introduction to regression analysis. We have done linear regression, and this is a video on binary logistics. So what is binary logistics all about? Like we said, supposing you want to predict the chances of a student entering into university or getting a scholarship into university, and then you have set of variables like a set of predictors like age, the examination score of the student, like gender, like country. So these are potential. I say potential because in the end, not all of them may be actual predictors. Some of them may not be predictors. So you have a list of potential predictors and you want to see which of these predictors can have an effect on chances of getting admission. So that is one example. This is an example. Supposing you have hemoglobin level, total white blood cell count, HIV status, and immunoglobulin G levels. You want to know which of these variables, assuming your outcome is HIV status, that is, the patient has HIV or does not have HIV, which you can say is HIV negative. So it's either HIV positive or HIV negative, coded as 0 and 1, 1 for HIV positive. So assuming we want to say that we hypothesize that HB, TWBC, and IgG are predictors of having HIV. These are hypothetical data, so they may not, of course, be true in real life scenario. So we want to see if we're saying that HB levels can predict HIV status or can predict, excuse me, can predict having HIV, same with TWBC and IgG. So we run it on regression and then we check the odds of prediction. And of course, we check if the model is significant, we check the odds of prediction. But this is going to be a simple regression, so I would only be using the univariate analysis and I'll only be doing I'll only be predicting the HIV status with hemoglobin levels. So you go to analyze. So now look at excuse me, your HIV status is your HIV status becomes the dependent variable because it is the outcome. HB becomes what? The independent variable. So you analyze regression, see a couple of options, go to binary logistics, and it's because I've been here already. So let's assume you just come here. This is how it will look. They will be empty. So your dependent variable is HIV status. You insert it or you slot it in. And what is your independent variable? HB levels. So you slot it in. Now you can see block 1 of 1 because sometimes you might want to compare more than one blocks, but again, we are in a simple regression analysis. So we go to categorical. This option is needed or important if one of your covariates is a categorical variable. For example, if you're having sex or gender, you would put it into this categorical covariate box. But we don't have any, or in fact, the only variable that we are using to predict is what? A continuous variable. So you go to other options. You might want to do osmolar goodness of fit test, but I don't want to do that. They are not that essential in interpreting um, um, your logistic regression. Many authors or many researchers will still do the statistics, but you have the freedom not to do it. So you check your confidence interval for the odds ratio, and then you click continue, and then you click your OK. So now you move on to, you allow spaces to do its thing, then you move on to the output table. So you'd see so many tables, and most of them are not that essential in interpretation. So there are just two tables I will take us through. The first is the omnibus test of model coefficient. Of course, like we add the ANOVA table in what? Linear regression. Here we have the omnibus test of model coefficient, the chi-square table, which will test the significance or the significant level of the model. It is telling us, is this model worth it? Is this model correct at all? Can we rely on this model? What is the model? It's the model is anything that you are the hypothesis you're testing. You're checking if HB can influence HIV status. So that is a model. So if the model is significant, it means that okay, yeah, HIV does have some potential to influence H to influence H. Sorry, I'm sorry. It means that HB does have some potential to do what? Influence HIV status, and we can rely on this relationship. But if the model is not significant, it's telling us that this relationship is not relevant, it's not important. Maybe HB is not what we should use. Maybe we should consider something else. So we can see that the model is significant. So we go to the variables in the equation table. So you have your B value for your HB, and you can see is negative 3.90. What is this telling us? Moving forward, you have your odds ratio written as exponent of B, simply obtained by exponenting this B. What this tells you is that, so what this means is that increasing the HB level or a change in the hemoglobin level decreases the chance of having HIV by negative 3.90. So this B value is simply the strength and the type of association. So if it was positive, you would say it increases the chance of having HIV by maybe 0.3, 0.90, but if it is negative, it decreases the chances of having HIV by 3.90. Another way you can interpret your binary logistics regression is with your odds ratio, sorry. And of course, it's the most common way of interpreting um, binary logistics. So they have similar information, but what you should know about odds ratio is that odds ratio is is interpreted in three ways. If the odds ratio is less than one, it shows a negative relationship, or yeah, negative relationship. With this one, it means that there is no association, there is no prediction. If it's greater than one, it shows a positive prediction. So you can see the odds ratio is 0.677, and is what? Less than one. So we say that um, increase or change in HP level would mean that the participant is 0.677 less likely to fall into or to develop HIV. So let me take that again. That a change in HB level would imply that the participant is 0.677 less likely to develop HIV. So I'll take that for the third time, please. What this means is that an increase or a change in HB level will mean that the patient or the study participant will be 0.677 less likely to develop HIV. So these are this you have your 95% confidence interval for the odds ratio. So remember that if you are using the odds ratio for univariate statistics, it is we call it the crude odds ratio. But if you're reporting the odds ratio of a multivariate statistics, it's called adjusted odds ratio. And we have talked about this already because you'd be adjusting for what? Confounders. So most authors, most researchers will report the odds ratio and the 95% confidence interval for the odds ratio in their research. So other parameters here are the standard error and the statistics, called wild statistics, just like we have your F ratio and your t-test value.